Washer method. The washer method is a type of volume of evolution, and you may want to learn the disk method before it, as the disk method kind of builds the washer method. So, given the problem f of x is equal to x to the third, and g of x is equal to x, and you want to figure out the volume of the region bounded by these two graphs as it rotates across the x-axis. So, let's graph these two graphs. Okay, with the graph drawn out, let's really think of what an integral is. When you learn about an integral, you kind of also learn about Riemann sums. And if you've forgotten, Riemann sums is approximating the area under a graph using rectangles. So as the width of these rectangles becomes smaller, the area it gives us for the area under the graph becomes more accurate. And for the integral, we learned the basic structure looks something like the integral of f of x times d of x, where the d of x represents the rectangle's width when it's infinitesimally small, and the f of x represents the rectangle's height. So, this integral operator is the same as this summation operator, but we don't have to write the limit of n approaching infinity, where the summation of I equals 1 going to n of f of x of I of delta x, where delta x is equal to b minus a over n, and x of I, or x initial, is equal to a plus I delta x. This just makes this a lot simpler and a lot nicer to just kind of see. Where this d of x is this delta x here, but the delta x, in this case, would have to be infinitesimally small to be this delta x. So now knowing that the f of x is actually just these lines that kind of come down from the graph at every single point, at every single region, to kind of find the area under the graph, we can use these lines, these individual lines, as the radius of the circle that we will form as we want to rotate this pink region across the x-axis to form this kind of circle. And then the washer method was going to make another circle for this blue region, where this blue region will cut into the pink area, the pink circle's area. So now let's look at what the formula will look like. The area of a circle is equal to pi r squared, and shown from down here, the r is the y value, or f of x or g of x, because they are telling us the radius of the circle, as they are the heights that are going to be rotated across the x-axis. And knowing that the integral is the sum of all these lines together, we can kind of just do the formula. The integral of pi f of x squared of d of x from these two regions, from 0 to whatever this region is. And we can figure out what this region is by setting f of x equal to g of x, or x to the third equal to x. And we find that x actually equals 1. So this will be bounded from the region to 0 to 1. So you may be wondering about this area here. When you were learning about the integral, you kind of learned that this area would actually be negative. But when finding volume, you don't want this negative, so you had to put an absolute value. Though for washer method and disk method, as the functions are being squared, you don't need this absolute value. So we can set the lower limit of the integral to -1, as this part is -1. And remember, whenever there is a constant within an integral, you can always take it out. So this will be pi times the integral from -1 to 1 of f of x squared dx, where f of x is x cubed. You can simplify this more by combining the x cubed squared to x to the 6th power. So now let's find the integral of this red region. The integral of this red region should be pi of the integral from -1 to 1 of g of x squared dx. And this is due to the same logic as this above. This will turn to pi of the integral of -1 to 1 of x squared dx. Now we need to subtract these integrals from one another. And this can actually convert to pi of the integral of 1 to -1 of x to the 6th power dx minus integral of -1 to 1 of x squared dx. And because we know the rules of integration, we can combine these integrals, as these integrals have the same bound. So this would be pi times the integral of -1 to 1 of x to the 6th minus x squared dx.